Now it's time to find an open entrance, check for the closest gateway in that direction and build the path towards that gateway. And to find an entrance, we open up a point cloud with the data from the third input. And as position, we use the origin plus the direction vector times 4. That means we always start in the center of the gateway and move 4 panel width towards the direction we randomly choose. And at that location, we're going to search with a radius of 1 and only need to find 1 point. And at this point, we increase the value of the variable try, another failsafe to exit the loop under certain conditions. But before we're going to use that, we check if our point cloud found any points. And that will only be the case if there is in fact a corridor in that direction. But as you remember, this will also be true for the entrance we originally came from. But there's a simple check we can do to prevent that this condition will be true in that case. And the statement for that condition is taking the inverse cosine of the dot product from the vector dir and the vector last dir multiplied by -1. And only if that inverse cosine is not 0, then we are allowed to use that entrance. So why does that work? If this was our original direction, and by chance the random vector that got selected is pointing back where we came from. Now if we multiply the last direction by -1, it is also pointing back, and the inverse cosine of the dot product from 2 identical vectors is 0. In any other case, we would get a different value. And that's the real condition when we want to set the variable foundDir to something that breaks the while loop. But instead of 1, we give it the value of the selected direction. But don't hit apply just now. We once again run in danger of creating a deadlock, because now our loop exit is behind a condition. If there's a point where this condition would never be true, we never exit the loop. And in fact, we would reach that point every time. Every time we reach the dead end of the path. If there's only one connection to a gateway, it can only be the way we came from. And that means the inverse cosine will be 0. And that is when we can use the failsafe. If we reached this point and the variable try is above 10, we can be fairly certain that we tried enough combinations and that we probably found a dead end. But now that we have found our direction, we still need to find the closest gateway. And that's when we create our second point cloud. This time we are looking at the center points of the gateways itself. We start at our current origin and we are looking with a wide range and also allowed to save multiple points. Now this point cloud is supposed to grab almost all of the points, at least all the points that could be relevant. After the cloud is opened, we loop over it with pciterate and the cloud handle. Then we import some attributes from the current point. For one, the position, and second, the point number. Now the point that we get from the cloud could be any point. There even does not need to be a connection to it. So how can we be sure that the cloud is showing us the closest gateway in the wanted direction? And the solution is simple. We just use the inverse cosine again in the exact same way. But this time it's the dot product of foundDir and the normalized vector of the position from the cloud point minus the origin position. And if it is the gateway we are looking for, the found direction and that normalized vector are pointing in the same direction. And as we already learned, if that's the case, the result of that whole operation is 0. And when we finally reach this point, we can create a new point at the position of the cloud point. That position then becomes the new origin. Then create the other vertex on the polyline using the new point. And before leaving this section, we also save the found direction as the new last direction. And now, very important, after these assignments, we need to leave the pciterate while loop with a break. Assuming we started at the gateway number 2, all of these conditions are true for both of these gateways. But the way pciterate works, we will always get the closest points first. As soon as we find a dead end, the value of try increases up to 10, and then we also leave the while loop. But there's a good chance that we find it before the for loop reaches the max steps. Now we could optimize this even further. When going for the next iteration of the for loop, we could check the value of try, and if we already reach 10, we would use another break to also escape the unnecessary iterations of that one as well. And you should definitely do that if you would use this setup in a setting where you have to deal with thousands and thousands of points. Then it would actually make a difference. But just for you to understand how quick this operation is, if we would have created a deadlock and printed out the value saved in add, which we increased in every iteration, it would not even take 1 second for that counter to rise above 1000. But let's see what this Pathfinder can do. By changing the seed, I get completely randomized variations beginning from a random point to any of the possible destinations. When taking a look at the incoming center points, I can look for the point number of a desired starting point, type that into the origin parameter, and now I get all the possible paths that start from that point.